The optical telescope is the foundational instrument of observational astronomy, and it performs three distinct functions that popular accounts often run together. First, and most important, it gathers light. A larger opening, the aperture, intercepts more photons each second, so that fainter objects can be detected at all. Second, it resolves detail because a larger aperture bends light through a smaller angle and so forms a finer image. Third, it magnifies, but for astronomy this is the least important of the three, since a star remains an unresolved point at any magnification, and what limits the astronomer is almost always the grasp of light and the sharpness of the image, not its scale. Of these, light-gathering power is the great driver of telescope design, and it scales with the collecting area of the mirror or lens, that is, with the square of the aperture's diameter. Because area grows as the square of the diameter, doubling the aperture quadruples the light collected. The famous 200-inch Hale telescope, dedicated in 1948, gathered almost exactly 4 times as much light as the 100-inch instrument it superseded, precisely the square of the ratio of their diameters. This square law scaling is the relentless engine behind the growth of telescopes. For every new generation of fainter, more distant, or more swiftly changing targets demands proportionally more glass. A single 8-meter telescope of the Very Large Telescope can record objects some 4 billion times fainter than the unaided eye can see, a reach bought entirely with aperture. Magnification, the function that most captivates the public, is the most easily understood and the least important for research. For an eyepiece it is merely the ratio of the telescope's focal length to the eyepieces, but magnification cannot conjure detail that the aperture and the atmosphere have not already delivered. Push it too far and the image only grows dimmer and blurrier, an effect aptly named empty magnification. For professional work the eyepiece is dispensed with altogether. The modern telescope is not a standalone viewing instrument but the front end of a system. It feeds a focal plane where the light is dispersed by spectrographs, sampled by silicon cameras, or relayed onward into adaptive optics and interferometric instruments. To understand a telescope is therefore to understand both the optics that form the image and the way that image is delivered to the instruments waiting behind it. There is a second, deeper reason to build large. Even a perfect, flawless telescope cannot form a truly point-like image of a star because light is a wave, and the finite aperture diffracts it, spreading each point into a tiny disk ringed by faint halos. The smallest angle a telescope can resolve shrinks in proportion to the wavelength of the light divided by the diameter of the aperture, so that a larger mirror, or a shorter wavelength, yields a sharper image. For the Hubble Space Telescope this diffraction limit is about a 20th of an arcsecond. For the 39-meter extremely large telescope now rising in Chile, it is some 16 times finer still, provided, as a later chapter will show, that the blurring of the atmosphere can be defeated. Longer wavelengths need larger mirrors to reach the same sharpness, which is why infrared and radio telescopes must be built so much bigger than optical ones. The first astronomical telescopes were refractors, using a convex lens to bend light to a focus. Galileo did not invent the instrument. Dutch spectacle makers had filed for it around 1608, but in 1609 he built his own and turned them upon the sky, discovering the 4 great moons of Jupiter, the phases of Venus, the craters of the Moon, and the countless resolved stars of the Milky Way, all through apertures of only a few centimeters that magnified some 30 times. Small as they were, these instruments overturned 2,000 years of belief in a perfect and changeless heaven, for here was a moon of mountains and craters, and a Jupiter attended by moons of its own that plainly did not circle the Earth. Yet the refractor carries a fundamental flaw, chromatic aberration. Because a simple lens bends blue light more strongly than red, it brings the colors to a focus at different distances, smearing every star into a colored halo. Early astronomers fought this by building absurdly long, spindly telescopes, their focal length stretched to dozens of meters to soften the error. The true remedy came with the achromatic doublet, which pairs a converging element of one glass with a diverging element of another, so that 2 colors are brought back to a common focus. The great Yerkes refractor of 1897, with a 40-inch doublet ground by the optician Alvan Clark, and a tube more than 90 meters long, remains to this day the largest refracting telescope ever built for astronomy, and it marks a hard physical ceiling. A large lens can be supported only around its rim, so it sags under its own weight and distorts. Any flaw or bubble deep within the glass cannot be polished away, because the light passes through the whole volume rather than merely glancing off a surface, and the long focus needed to tame the residual color makes such instruments impossibly ungainly. No larger refractor has been built since, nor ever will be for research. The future belonged to the mirror. A reflecting telescope forms its image with a curved mirror instead of a lens, and this single substitution abolishes chromatic aberration entirely, for reflection bends every color identically. Isaac Newton, exasperated by the color errors of the refractor, built the first practical reflector in 1668, using a small metal primary mirror and a flat secondary to divert the beam out the side of the tube to an eyepiece, the arrangement still called a Newtonian. A mirror can be braced across its entire back surface, so it does not sag as a rim-held lens does, and only its front face need be figured to perfection, so flaws within the glass are of no account. These advantages made every great telescope of the 20th century and beyond a reflector. Reflectors are not free of aberrations, however, and the story of their design is the story of cancelling those errors one by one. A simple spherical mirror suffers spherical aberration, focusing the rays from its edge at a different point from those near its centre. Newton's little spheres were tolerable only because their apertures were so tiny. Shaping the primary into a paraboloid removes spherical aberration for light on the axis, which is why the classical research reflectors adopted parabolic mirrors, but the paraboloid brings its own defect, coma, which flares every off-axis star into a small comet-shaped smear, and so narrows the usable field of view. The Cassegrain form, devised in the 1670s, folds the light path with a convex secondary that sends the converging beam back through a hole in the primary, yielding a compact tube with a long effective focal length. The decisive refinement came around 1910, when the American optician George Ritchey and the French astronomer Henri-Chrétien conceived a design using hyperbolic curves for both mirrors, their shapes tuned so that coma and spherical aberration cancel together. The resulting Ritchey-Chrétien telescope delivers sharp, coma-free images across a far wider field, and it has become the standard geometry of serious astronomy. The Hubble Space Telescope, the Keck telescopes, the Very Large Telescope, and essentially the coming giants are of this form. Wide-field instruments add corrector lenses near the focus to tame the residual curvature, but it was the coma-free field of the Ritchey-Chrétien that made it the workhorse of the modern observatory. A great modern reflector routes its light through 3 or more shaped mirrors, reaching a focus behind the primary or diverted by a flat tertiary out to a azimuth platform on the side of the mount, which stays gravitationally steady and can carry massive, instrument-laden benches that could never be hung at a moving focus. A third family, the catadioptrics, marries mirror and lens to win wide fields beyond the reach of a bare paraboloid. The Schmidt camera, invented around 1930, places a thin, delicately shaped corrector plate before a simple spherical mirror, introducing exactly the opposite aberration and so yielding an exceptionally wide, sharp field. Schmidt cameras became the workhorses of the great photographic sky surveys, and their descendants, the Schmidt-Cassegrain and the Maksutov, are familiar to amateur astronomers the world over, wide-field mappers rather than deep-pointing giants. The great Palomar Sky Survey of the 1950s was made with such a Schmidt, and the wide-field survey telescopes of today, which sweep the whole sky again and again to catch whatever moves or flares, inherit its philosophy directly. A telescope must not only point anywhere on the sky, but then track its target as the Earth's rotation carries it steadily westward. The mechanical structure that does this, the mount, comes in 2 fundamental forms. The equatorial mount tilts one of its axes to lie parallel to the Earth's own spin axis. Tracking then requires turning only that single axis at a constant rate, the target holding still in the field while the field itself does not rotate, a great virtue for the long photographic exposures of the past. The German form of this mount, with the telescope on one end of an axis and a counterweight on the other, was developed by Joseph von Fraunhofer for a great refractor completed in the 1820s, and for more than a century, the equatorial mount was universal for large telescopes. The rival altazimuth mount moves in the 2 intuitive directions of up and down and around the horizon. It is mechanically simpler, far more compact, and much stiffer for a given mass, a decisive advantage as apertures grow into the many-meter range, but tracking a star demands that both axes drive at continuously varying rates, and the field of view slowly rotates about the target as it goes. What tipped the balance was the computer. Once a processor could compute and command those 2 changing rates in real time, and a rotating platform could cancel the turning of the field, the mechanical superiority of the altazimuth became overwhelming. A Soviet 6-meter telescope of the 1970s was the first large instrument to use a computer-driven altazimuth mount, and every large telescope built since Keck, the Very Large Telescope, and all three of the coming giants, has followed. The stiffer, more compact mount also shrinks the dome, whose cost climbs steeply with the volume the telescope must sweep. As mirrors grew larger, a new problem arose, and its solution is one of the quiet triumphs of modern telescope making. A mirror thick enough to hold its own shape under gravity becomes impossibly heavy, much beyond 8 meters, so the great mirrors of today are deliberately made thin, or built from many segments, and held in their precise figure by active optics, a system of computer-controlled actuators behind the glass that, guided by measurements of a star's light, gently push the mirror back into shape as it tilts and cools. This slow correction of the telescope's own figure, working over seconds and longer, must not be confused with the far faster correction of the atmosphere that a later chapter describes. Active optics is what makes the thin and the segmented mirror possible at all. For a telescope on the ground, it is usually the atmosphere, and not the optics, that sets the sharpness actually achieved. Turbulent cells of warm and cool air smear a stellar image into a dancing blur far larger than the diffraction limit, so that without correction a 10-meter mirror sees no more sharply than one of 15 centimeters. It merely gathers vastly more light. The technique that defeats this blurring, adaptive optics, measures the distortion hundreds or thousands of times a second, and reshapes a small deformable mirror to undo it, often using a laser to conjure an artificial guide star high in the air. It now lets a ground-based giant rival Hubble's sharpness in the infrared. This is the subject of its own chapter, and it is built directly into the optical path of every extremely large telescope. A telescope is only as good as what records its light, and here the late 20th century brought a revolution as consequential as any mirror. For 100 years the photographic plate was the standard medium, yet it captured barely 1 photon in 100. The charge-coupled device, a silicon chip that turns photons into trapped electrons, raised that yield to some 80%, capturing 30 to 100 times as many of the available photons, an improvement equivalent to multiplying every existing telescope's aperture several times over without touching a single mirror. Being also linear, digital, and precise, the charge-coupled device made possible the exact measurement of brightness and the computational image processing on which all modern astronomy now depends. With the physics in hand, the story becomes one of ever greater instruments, and the 20th century's great reflectors mapped the very structure and expansion of the universe. George Ellery Hale, the most consequential telescope builder in history, drove the construction of one record aperture after another. At Mount Wilson in California, the 100-inch Hooker telescope saw first light in 1917, and with it, in the 1920s, Edwin Hubble resolved individual stars in what had been called the spiral nebulae, proving them to be separate galaxies far beyond our own, and then found the relation between a galaxy's distance and its speed of recession that first revealed an expanding universe. Hale's final and grandest project was the 200-inch telescope at Palomar, its mirror cast in 1934 from a new low-expansion glass to resist the distortions of temperature. Dedicated in 1948, a decade after Hale's own death, it reigned as the most powerful telescope on Earth for nearly 30 years. But the Hale mirror was about as large as a single thick disk of glass can practically be made. To go further, telescope makers would have to abandon the monolith altogether. The breakthrough came from Jerry Nelson and his team in California. Rather than cast one impossible giant, build the primary from many smaller hexagonal segments held in perfect alignment by active optics. The twin Keck telescopes on Maunakea in Hawaii each assemble a 10-meter mirror from 36 hexagonal segments, every one less than 8 centimeters thick, continuously nudged by actuators so that the whole surface behaves as a single flawless curve. The first Keck saw light in 1990 and began its science in 1993. The segmented mirror, it proved, is the direct ancestor of the giants now under construction. A parallel European path took a different route, emphasizing thin monolithic mirrors and the power of combining several telescopes at once. The Very Large Telescope, high in the Atacama Desert of Chile, is built of 4 8-meter telescopes, each with a thin, flexible mirror held true by active optics. Any one of them alone can reach almost unimaginably faint objects, but the array's signature power is interferometry. the light of the separate telescopes can be combined so that together they achieve the fine angular resolution of a far larger aperture, an approach precise enough to have tracked the orbits of individual stars around the black hole at the center of our galaxy. 4 smaller movable auxiliary telescopes feed the same interferometer, so that the array can fix a star's position to within a few millionths of an arcsecond. Between them, Keck segmentation and the very large telescope's thin mirrors and interferometry define the 2 engineering philosophies that the next generation would scale up. 3 projects now aim to roughly quadruple the aperture of today's largest telescopes, entering the era of the extremely large telescopes. The greatest and most advanced is the European Southern Observatories' extremely large telescope, under construction on a Chilean mountaintop near the Very Large Telescope. Its 39-meter primary is assembled from 798 hexagonal segments, each polished to within a few billionths of a meter of its intended shape, and held in place by thousands of edge sensors and actuators. A 5-mirror design builds the atmospheric correction directly into the telescope itself, and its images will be some 16 times sharper than Hubble's. The observatory plans its first light late in the 2020s, though, like every great instrument schedule, that date remains subject to revision. The giant Magellan telescope takes the opposite approach. Instead of hundreds of small segments, it uses 7 of the largest stiff mirrors ever cast, 6 of them arranged around a central 7th like the petals of a flower to form a single surface some 25 meters across, each mirror spun from 16 tons of glass and polished over years. It too is rising in the Chilean Andes. The 30-meter telescope would build a 30-meter mirror from nearly 500 segments, an international project of great ambition, but its situation is genuinely unsettled, and honesty forbids reporting it as a routine construction schedule. Its preferred site on Maunakea is sacred to many native Hawaiians, whose sustained opposition has repeatedly blocked construction despite the court's approvals. An alternative site in the Canary Islands has been studied, and in 2025 a major funding body declined to prioritize it, casting real doubt on its future. The 30-meter telescope stands as a reminder that the limits on a great telescope are not only optical and mechanical, but financial, political, and ethical. The headlong pursuit of ever greater aperture is justified by 2 scaling laws acting together. Light grasp grows as the square of the diameter, and for a telescope corrected to its diffraction limit, the gathered light is concentrated into a core that shrinks with aperture as well, so that the power to detect a faint point of light against the sky climbs very steeply indeed. With size, this is why the coming giants promise not a little, but as much as an order of magnitude more sensitivity and resolution than today's best. Their frontiers are concrete: to capture the light of rocky planets in the habitable zones of nearby stars and search their air for the molecular signatures of life, to witness the formation of the first galaxies in the early universe, to weigh the black holes at the hearts of galaxies by the motions of the stars around them. They will also sharpen, without any guarantee of settling, the deepest, open questions: the disputed rate of the universe's expansion, the so-called Hubble tension, and the true natures of dark matter and dark energy, which remain genuinely unknown. The optical telescope's 4-century journey from a few centimeters of glass in Galileo's hands to a 39-meter mirror held in shape by thousands of actuators and corrected against the atmosphere 1,000 times a second, is a story of physics relentlessly applied, each barrier, once understood, becoming the next engineering target in the oldest quest of observational astronomy, to gather more light more sharply from farther away.